All right, welcome back, and I hope you had a good break. So we are still discussing section 14, and under section number 14, so far we've been looking at two-dimensional and three-dimensional, right? So we have looked at areas and volumes. That was the first part of the video. Now, the second part of our discussion is when we focus on dosage calculations. Now, this will be the last video, and that will cover carbon dioxide emissions. So carbon dioxide emissions. Now, carbon dioxide, or CO2, as a chemical formula for carbon dioxide, is one of several greenhouse gases in the Earth's atmosphere. Now, in a typical greenhouse, glass permits light from the sun to enter, but traps the heat generated by the sun's light within the enclosed space, allowing the plants to grow, all right, and thrive. Now, here, if you remember, this is still a math class, though. This is not a science class, but this is very important concept for us to know. If you remember, if you did something on photosynthesis, right? Photosynthesis. Now, plants give out oxygen, all right? And then humans give out carbon dioxide. Is that okay? So plants need carbon dioxide in the preparation of their food in the process called photosynthesis. And then humans will in turn take in the oxygen given by plants. So there's a popular saying in science that when the last three dies, when the last tree dies, the last man is going to die, because there wouldn't be a balanced amount of CO2 and oxygen in the atmosphere, right, for that to be a proper exchange. And so humans are going to die when the last plant dies. So we are encouraged to grow more plants, okay, so that we can have a balanced ecosystem. Now, in our atmosphere, carbon dioxide and other such gases let light from the sun to hit the earth and warm the surface. And like the glass that encloses the greenhouse, these gases trap heat, and it's from escaping into outer space. Okay, now they play a key role in maintaining the delicate balance that keeps our planet warm and full of life. All right, so if you are somebody who is more concerned about the environment, the amount of CO2 in the atmosphere must be of concern. All right, we talk about, these days we talk about the global warming and all kinds of environmental degradation effects of humans. And here we are going to get into how we can, see what really happens, our day-to-day contribution towards the amount of CO2 in the atmosphere. Is that okay? Now, with this knowledge, you should begin to see why producing CO2 might be important to our lives. Okay, nice. So here is a graph, the global carbon dioxide emissions of fossil fuel burning from 1751 to 2012, right? And over here, this is million tons of CO2, and we have the years. All right, now let's do some analysis on this graph. Now, what are some fossil fuels? And fossil fuels, we have what? Coal, oil, natural gases are some examples of fossil fuels. What observations can you make about this graph? What can you see from this graph? You realize that the amount of carbon dioxide keeps increasing, right? So since 1950, the amount of CO2 being released into the atmosphere has dramatically increased each year. Due to burning of fossil fuels, the increased CO2 can lead to an increase in Earth's average temperature, right? So we talk about that later in the course. Now, would you say that this follows a linear or exponential? Look at it, all right? And this has something to do with section number 8. So this really has an exponential growth, right? Now, estimate the global carbon emission from 2012. All right, so the title says the last year represented the 2000, so it is estimated value of the end of the graph. So that is about 9,800 million tons of CO2. That's a lot, right? So it keeps growing. Now, estimating CO2 emissions from burning gasoline. Now here we are going to know that as you drive around, you are contributing to the amount of CO2 that is being generated, right? So we are going to see that as well. And later in the page, we're also going to see that even charging your phone using an electrical appliance, all right, also contributes to the amount of CO2 in the atmosphere, all right? So we will look at your impact, all right? Now we are in the age of technology, and many of the things that we do are through gadgets, and they contribute to CO2 in the atmosphere. Now we will start with some information about gasoline. 1 gallon of gasoline weighs 6.2 pounds. So a gallon of gasoline has a weight of 6.2 pounds. Now a gallon of gasoline is about 87% carbon. So a gallon of gasoline contains 87% carbon and 13% hydrogen by weight. Now, how many pounds of carbon are contained in a gallon of gasoline? So what do? We will change the percentage to a decimal, and that gives us 0.87. Then we multiply by the weight of a gallon of what? Gasoline, and that gives us 5.4 pounds of CO2. All right, now we want to change this into kilograms. So this result that we have here, we want to look at it in terms of kilograms. All right, and we know, going back to pages 2 through 5, our formula sheet, 1 pound is approximately 0.4536 kilograms, and that changes to 2.45 kilograms of carbon, right? Now we want to look at hydrogen, right? Now 13%, a gallon of gasoline contains 13% of hydrogen. So therefore we will change that to a decimal and multiply and know how many pounds of hydrogen are there in a gallon of gasoline. Okay, we want to change that as well. Okay, now here, the hydrogen released into the atmosphere from burning gasoline combines with oxygen to form water. All right, so a water molecule has 2 hydrogen atoms. So we have 2 hydrogen atoms and has 1 oxygen atom, right? Now, the atomic weight of oxygen is 16, and that of hydrogen is 1. And that combines to what? So we find the molecular mass. You don't have to know this. This is chemistry, but we will just be interested. You'll not be asked to do that. Okay. And that will give you 18. Okay, that is why we have 18 right there. Now, we want to estimate how much water a gallon of gas produces when burned, and we multiply. Remember, we found that of H2O, and that gives us that. So that is some science of the whole process. All right. Now, we talk about CO2, and then CO2, carbon has an atomic weight of 12, oxygen has an atomic weight of 16, so we have CO2, which is 12, okay, plus, and then because we have 2 atoms of that, and that gives us 44. That's why we have 44 right there. Our focus is not to find the atomic weight or molecular mass or whatever, okay? But we are going to be looking at this. Now, so if you look at this and you go back to pages 2 through 5, the formula sheet, okay? CO2 from gas, 19.8 pounds per gallon, okay? So you produce 19.8 pounds of CO2 for every gallon of gas you consume. Is that okay? And we are going to use that. So that's what we need. So burning a gallon of gas produces 19.8 pounds of CO2. So every gallon of gas you burn, all right, you produce 19.8 pounds of CO2. That's your contribution for consuming a gallon of gas. Now we are going to look at your commute. As you commute to school, you look at how much of that you produce. So how can this information be written as a unit fraction? So a gallon of gas produces 19.8 pounds of CO2. All right, and that is the standard unit. Now, if you, I'm talking about you, use 30 gallons of gas a week to get to school, how much CO2 is emitted by your commute? Tell me about it. Okay, so you know that a gallon of gas, so 1 gallon produces 19.8 pounds of CO2. So if you consume 30 gallons of gas in a week, we want to know how many pounds of CO2 you generate, right? And that is how much of CO2 you produce per week. Okay, so you as an individual produce 594 pounds of CO2 per week. Okay, nice. So if you do more than that, you can estimate that. Now, if the tank of a car holds 40 liters of gasoline, how many pounds of CO2 are produced by burning an entire tank of gas, right? Now we know that a gallon, you produce 19.8 pounds of CO2, okay? Now, we are not dealing with liters, so that should tell you that you have to change from liters into gallons. Is that okay? You have to change from liters into a gallon. Now, so changing this from liters, so you have to change liters to the gallon. How do you do that? Okay, so do that. So now you know that if you go on your formula sheet, the third page, you know that there's no direct relationship between liters and gallons, but you know that 1 quart is approximately 0.9464 liters. Now you have 40 liters. How many quarts would that be? So that is how you change. So your X is going to be 40 over 0.9464. And that would change liters into what? Into quarts. So your answer right here will be in quarts. Is that okay? So this should give you 42.3 quarts. Now you realize that on the first table on pages 2 through 5, you know that a gallon is 4 quarts. Now you have 42.3 quarts. You want to know how many gallons are there. So let me say that is y. Now you divide and divide, and right there you cross product, right? So your y is going to be 42.3 quarts divided by 4, and that will give you the gallons. Is that okay? So what do you have for that? So that should actually give you 10.57 gallons, right? I think so. And you should get the gallons, and now you can multiply by 19.8. So this is going to give you the number of gallons. So your goal was to change from liters into gallons. So 42.3 divided by 4, yes, that should give you 10.575 gallons. Now you can multiply this number of gallons by 19.8, and that will give you how much of CO2 that you have produced, okay? So this, what I did was the step-by-step approach, and if you want to go one shot using the factor label method, that is how you do that, okay? Nice. Now, if a car gets 26 miles to the gallon on average, how much of CO2 is emitted into the atmosphere when that car travels 100 miles. Okay, so this means the car that's 26 miles, and that car will consume a gallon of gas. Okay, so for every 26 miles traveled, you need 1 gallon of gas. Is that okay? Now, if you want to know how many gallons you need for 100 miles, what do? You just divide 100 by what? 26. Is that okay? And what does that give you? So 100 by 26, and that will give you the number of gallons you need. So you need 3.85 gallons gas. Is that okay? But you also have to know that a gallon of gas produces 19.8 pounds of CO2. So you multiply that amount by 19.8, and that gives you the amount of CO2 produced. Okay, sounds good. And this is the factor label method used very nicely to produce the results. Number 5, if a car gets 30 miles per gallon on average, how much of CO2 is emitted? So 30 miles per gallon, right? So you just do 30, okay? And then you multiply by that. Is that okay? Nice. So that is how much of CO2 that you emit. Is that okay? Nice. So that's basically how you do that. Is that okay? Nice. Now right here, we want to look at, so having looked at how much of CO2 is produced by burning gasoline, now we want to look at how we can estimate CO2 emissions from electricity usage. So when you receive your electricity bill each month, your usage is most likely presented in terms of kilowatts hour. A kilowatt hour is a unit of energy equivalent to 1,000 watts of electricity used for 1 hour. So for example, if you left a 100-watt light bulb on for 1 hour, you would use that. So really, you have to change watts into kilowatts. So therefore, you divide by 1,000 and then multiply by the hour. And this is how much, 0.10 kilowatts hour. Is that okay? Nice. So that is how you do that. So for this, whatever watts we are given, we have to change that into kilowatts. And then we will multiply by the national average. So the national average is 1.37 pounds of CO2 per kilowatt hour. So that is also on your formula sheet. So if you're still on pages 235, okay, that is under the carbon dioxide emissions. So let's look at that. So that is the national average for electricity usage, how much of CO2 is produced, okay? Kilowatt hour. Okay, nice. Now right here, we want to look at 2 appliances. Is that okay? So here, the wattage of an electric oven is approximately 3,000, and that of a crock pot is 250 watts. Now we want to find the kilowatt hour for cooking a chicken in the oven for 2 hours and in a crock pot for 5 hours. So for the oven, we have to do that. So we divide by 1,000 just to change it into kilowatts, and then we multiply by the number of hours that appliance was used, and that gives us 6 kilowatt hour. We do the same for the crock pot, okay? And now we want to assume that over a period of time, our cooking appliances are actually on 70% of the time. If we reduce our calculations by 30%, we have a comparative figures for our two appliances. Okay, so we multiply by what? 0.7. Okay, this is because, you know, when the oven is on, at some point it cuts, it breaks, all right, and then it starts heating again. Is that okay? So this is just to compensate for the period of time that the appliance is on the whole time, right? So nice. Now we want to calculate the amount of CO2 emitted by the oven and the crock pot. Okay, so we have to multiply by the national average of 1.37, and that is that. Okay, so which option, the oven or crock pot, is greener? So it's pretty clear that the crock pot is much more greener than the oven. Okay, nice. All right, sweet. Now this is a table you have in your book, all right, on pages 181, and we are going to refer to some of these appliances. Okay, we are going to make reference to some of these appliances. So this is these are the appliances. Okay, living room appliances, office appliances, cleaning, bedroom. Okay, and their corresponding watts that they use. Okay, so that is on page 181. So yep. Now, okay, it's your turn. Think through each problem below and estimate the CO2 emitted in the following situations. Now, use how much power do your appliances use? Okay, table located page 103 for the wattage, right? Now, how much CO2 is produced from using a game console for 5 hours? A game console for 5 hours. So look at the page, the table on 181, and locate a game console. So a game console is under living room, right? So under living room, you realize that a game console has 50 watts. So you change to kilowatts by dividing by 1,000, and you multiply by how long you use the game console, and then you multiply by the national average. And that gives you how many pounds of CO2 is produced from using the game console for 5 hours. Is that okay? Nice. Number 2, how much CO2 is produced from ironing for 1 hour per week for 4 weeks? So if you are still on pages 181, are you able to locate the iron? So are you able to locate that? Okay, so under cleaning, you have clothing iron, right? Under cleaning, look under cleaning, and you see clothing iron, and that is 1,100 watts. You divide by 1,000 to change it to kilowatts. You multiply by how long you use the clothing iron for, and because you're looking at 4 weeks, you multiply by 4, and then you multiply by the national average of CO2 for electricity usage, right? And that gives you 6.0 pounds of CO2. Is that okay? Nice. Now, how much of CO2 is produced from an old refrigerator for a month? Assume the refrigerator is not drawing power 30% of the time. Now, if you look for old fridge under kitchen, on pages 181, old fridge under kitchen, that's 115 watts. Okay, you divide by 1,000 to change it into kilowatts, multiply by 24 hours. And this is for what, 30 days. Now, we are saying that this is not drawing power for 30% of the time. So therefore, it's drawing power for 70% of the time. So you multiply by 0.7, and then you multiply by the national average, and that gives you 79.4 pounds of CO2. Sounds good? Okay, Gucci. Now, number 4. If someone sleeps each night with an electric blanket turned on for 8 hours for the 4 coldest months of the year, how much CO2 is emitted? Okay. So if you look for a blanket, okay, are you able to find the blanket? So under bedroom, right? You look at electric blanket, and that is what? 200 pounds, 200 watts, sorry, 200 watts divided by 1,000 to give you that, and then 8 hours for 30 days, times 4 months, and then times their national average, and that gives you 263 pounds of CO2. Number 5, a dishwasher for 45 minutes. Now, because we are dealing with hours, kilowatt hours, you have to change 45 minutes into hours first. So you look for the dishwasher, and the dishwasher is under kitchen. All right, and dishwasher has 1,500. Okay, so 1,500, and you change 45 minutes into hours. So 45 over 60. Okay, and that gives you that. Okay, now you have that. Awesome. Now, what would be the CO2 savings from a ceiling fan for 8 hours instead of a 1-room air conditioner for 8 hours? So you work out these for a fan, a ceiling fan, and then you do that for AC, and then you find a difference. Is that okay? And that should be how much will be saved from CO2. Now, suppose the cost for electricity is 0.10 per kilowatt hour. So that's how much you pay for every kilowatt hour. Now, what is the cost for using a game console for 5 hours? Okay. So now you have to look for the game console. We already used that, right? So a game console is 50 watts, change to kilowatts, multiply by the number of hours, and then multiply by the costs per kilowatt hour. And that is how much you pay for the game console. Okay, for 5 hours. Sweet. Gucci. All right, I like that. Now, let's go and talk about something really very interesting, right? Some interesting conversation about energy vampires. Now, one more thing. When you turn off an appliance, it may continue to consume electricity. A large number of electrical products, from air conditioner to clocks, cannot be switched completely off without unplugging the device or turning it off at a power strip. Now, these products draw power 24 hours a day, often without the knowledge of the consumer. We call this power consumption standby power, but we call these products energy vampires. And this is what most of us are guilty of. I'm guilty of that. So really, if you are not using the appliance, you're supposed to unplug it from the power strip, right? So if you charge your phone and you leave your phone in the socket, it still draws some power, but that power is different from when you're actively charging the phone. All right, and that is what we call energy vampires. So on pages 182, there's a list, there's a table there that gives you how much of electricity is being used when the appliance is in standby mode. Okay, when you are not actively using the device, the table produces the amount of watts that is being drawn, okay, on your account when the appliance is not being used. Now, the standby power consumption is particularly inefficient designs can be as high as between 15 to 30 watts. Now, for a single appliance, this may not seem like much, but when we add up the power consumption of the billions of appliances in the US, the power consumption of appliances that are plugged in but not being used, this is very substantial. Okay, so a good takeaway, if you're not using the appliance, just unplug it. All right, because it draws some amount of power. So this is the table I was talking about. So this is when the appliance is in standby mode. These are the watts or the consumption, the amount of power these appliances consume when they are in standby mode. Okay, so the very few questions we're going to be looking at right now, we'll be looking at when the appliance is in standby mode. All right, so a computer is on standby mode half of the time for a year. How much of CO2 is emitted in the standby mode? So we realize, we look at the table and it says that when the computer is on standby, it consumes 2.84 watts of electricity. So we divide that by 1,000, multiply by 12 hours, 365, and by the national average. And yet some amount of CO2 is being emitted, right? Now, how many total pounds of CO2 does the computer produce over the course of the year? Okay, look at that. So here, the first part we are looking at when this is in standby. This is standby mode. So let me do standby. And this is active use. I'll call it AU for active use. So note the difference. Now, when we put the two together, when it's on standby and when it's in active usage together, that gives you that total. Is that okay? So I was talking about standby. All right. So suppose air conditioner is left on 24 hours. If you are charged 0.1 per kilowatt hour, that is how much you pay. Is that okay? Nice. So here, so far we've gone through carbon dioxide emissions from gasoline and CO2, and carbon dioxide emission by country. So here we are exploring, all right, looking at countries and how much of CO2 that is being emitted. So the global carbon emissions broken down by country. So that is what this really is about. And how are they similar, right? Same data is shown, only difference is the format. So here we use a pie chart and here we use the bar graph, but it actually depicts the same information. All right, so here we want to know how many pounds were produced in the United States. Okay, nice. And in the United States produced 15%. Is that okay? So, and for Japan, that is it. Okay, nice. So here we are looking at a pie graph versus a bar graph. So pie graph makes it easy to see that data is a part of a whole, but some of the pie slices are too small to be effective. Bar graph makes it easy to compare the data and could be recorded for emphasis. Okay, so this is, pie graph versus a bar graph. Okay, nice. And that's basically about it. Now, on this slide, this is taking you through how the step-by-step process to go through to create a bar graph. Okay, and it's as simple as that. So the instructions are quite clear, and go through this the instructions if you be able to create a bar graph. Okay, nice. So that is how that should be done. Now, here are practice problems for everything we have discussed so far when we spoke about areas and volumes, dosage calculations, and then we came to carbon dioxide emissions. All right, so these are practice problems for you. So make sure you do these practice problems and then you compare if these answers are right, okay? So try your hands on these practice, okay? Practice makes perfect. You only learn well by doing, so practice. So take your time, go through these one after the other and check Is that okay? Nice. So this is dosage calculation. So if a person weighs 250 pounds, how much of drug should each be given, right? Okay, don't forget that the standard is 25 milligrams per kilogram. So therefore, you have to change from pounds to kilograms. Okay, and then you multiply by the milligrams, the volume, and then because it's for 2 doses, you divide by 2. And yeah, how many ml are needed to give 1.5. So right, so you're changing from grams into milligrams, right? And then you multiply by 10 and divide by 400. Now, your friend uses 25 gallons of gas using this speedboat over the weekend. Approximately how much of CO2? So 25 gallons. And we know that the standard consumption or the standard for CO2 production is every pound or every gallon of gas, you produce 19.8 pounds of CO2. So if your speedboat is 25 gallons, you multiply by 19.8, and that gives you the amount of CO2 produced. Now, how much of CO2 is produced by driving 600 miles in an SUV that gets 38 miles per gallon? Okay, so 38 miles per gallon. So for every 38 miles, okay, the SUV consumes.
Sorry, I can't start or stop your car.
1 gallon of gas. Is that okay? So you have to change that. So you do 600 over 38. Sorry for that. That was my phone. Siri was trying to distract us. And then you multiply by 19.8 pounds of CO2. Is that okay? So suppose your water softener runs for 28 minutes every night. So you look for the water softener, right? And that is on pages 181. How many? What is there? That and the water softener, that's 2 watts. You change that and then you multiply. Okay, so basically, this is how the whole conversation has gone over areas and volumes. Okay, and dosage calculations and CO2 emissions. Okay, so on this note, I would like to thank you very much for your time. Okay, and have a good time, and I will see you soon. All right, bye-bye.